Alright, last couple that I'm going to do are looking at drug ionization percentages. These should be very straightforward too, but I know that people get thrown off a little bit by this. The idea is still using our Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of base over acid, or whatever. But the idea is that we're actually looking specifically for this. We're looking for that concentration ratio. So if we basically just solve it out from there, we can see that pH minus pKa is equal to the log, which is a base 10, of base over acid. And then we take that, and then we just say that 10 raised to the pH minus pKa is equal to base over acid. So this is our drug ionization formula, but it's basically just a derivative of the Henderson-Hasselbalch equation. So the idea is that if he's giving us a pKa, we should be able to solve for these in each of these areas, because he gives us the pH of the stomach, the small intestine, and then the blood. So the idea is that if we do 10 raised to the 2 minus 5.05 is equal to base over acid. So then we have to figure out, okay, which one is our ionized form, our base or our acid. If he gives you that the drug is acidic, more likely than not, the ionized form is going to be the base. You can see that by drawing it out if you need to. Warfarin plus H2O gives warfarin, can't even spell it today, minus plus H3O plus, because he said it's acidic or whatever. So this is our conjugate base, and this is our acid. So if this is our ionized form, then we know that this ionized form is what's on top here. So whenever we get this answer to this ratio, then we know that this is our ionized over acid in terms of like the answer that it gives us. And the reason that we just call acid 1 is because you can basically turn anything into a ratio. So we'll solve this real quick, and then I'll kind of show you what I'm talking about. So 2 minus 5.05, and then 10 raised to that is 0.000891251 is equal to base over acid. So the idea is that anything divided by 1 is the same number. So if I take this long ass number and divide it by 1, it's still the same number. And so division is basically just a formation of fractions. So when you have that formation of fractions, B is equal to that top number, and A is equal to that bottom number when you're using these fractions in terms of, figuring out your stuff. So when you're looking at it this way, you can say, well, if A is equal to 1 and B is equal to this long ass number, then you know that what your approximate amounts of each of these are. And then the idea is that your ionization percentage is just your ion concentration over the concentration of the non-ion plus ion concentration, and then times that by 100. So the idea is we're looking at the B, the base, being on top, and that is our ionized form. So therefore that's on top right here. So we do 0.000891251 over this same number. I'm just gonna put little quotation marks, because I'm gonna write that out again, plus whatever our non-ion form number would be. So we go back to this and we see that it's a 1. And then you multiply this whole thing by 100. Well, y'all can see that. Let me make sure y'all can see that. You can barely see that. There we go. Let's turn that down. So the idea is this will give us our percent ionization. So we will do second answer divided by second answer plus 1 times by 100. It's still very, very low. So basically in the stomach, because it is an acid, it's not going to be very likely that it's going to be ionized. So we end up getting a very small number of 0.89%. With the idea that it kind of makes sense, like something that's an acidic drug, you stick it in the stomach is more acidic, so therefore your drug is not going to be getting rid of its hydrogen because there's all this extra hydrogen in that area. So because it's not ionized, it's more likely to dissolve, or not dissolve, but it be absorbed in the stomach because it's an acidic drug. And then we basically do the same thing for each of the other body systems. So for like the small intestine, it is 10 to the 7.8 minus 5.05 is equal to 5.05, which equals 562.3413. So the idea here is that, okay, it means that there's quite a bit that is in its base form in comparison to its acid form. Because in comparison to its acid form, there's 562 more of the base than there is of the acid. So then we're looking at, okay, cool, which one is the ionized form? This base again, because we're still looking at the warfarin. So then we do our ion over total times 100. So the ion would be the 562.3413 over 563.3413, because it's plus 1 for the A, times it by 100, which then gives us, so divided by second answer plus 1, gives us 99.82%. So it's saying that there is almost 100% of this warfarin, that's an acid, ionized in the small intestine, which means that if it's in its ionized form, it's not going to absorb there as readily. So the idea is that because of that, we're looking at, okay, whenever it gets out of the stomach and into the small intestine, you know, it's ionized, so it's not going to pass those membranes. So warfarin, if it's like asked, I don't know what we asked for our class, but if it's asked in a future aspect, it's going to be like, where does it absorb? It's going to absorb in the stomach because it's an acidic drug, which is a lot of drugs are acidic drugs, not all of them are a lot. And then the idea is we're looking at the blood, and blood's pH is 7.4. So it's very similar to the small intestine, so it's probably also going to have a high amount of the drug ionized, which in the blood, that's a good thing because we need it to be ionized in the blood so that our body can actually carry it using either have it dissolved in our blood, which is a lot of water, or have it carried by some sort of carrier protein like albumin. So yeah, so I'm not going to do the blood one because it's basically going to be the same thing for as the small intestine one. So higher pH could be very, very ionized for an acid. Lower pH could be very, very non-ionized for that acid. And I'm just erasing because I don't have the room to do more of this. Okay, and then we're looking at like automate. So, I think it's kind of funny that he has like us trying to find out like, you know, like our pH in our stomach and small intestine and blood and all that different stuff for like automate, but whatever. So automate is a base, which means that it goes from B, which is non-ionized, to BH plus, which is ionized. So this is still our base form, and this is our acid form here. Okay? So then our idea is that if we're looking at this and we're trying to do our 10 pH minus pKa is equal to base over acid, we're actually changing where the location is of our ionized form. Now our bottom is our ionized form. So for automate specifically, let's say we're doing in the stomach. So we're saying that we're doing 10 to the 2 minus 4.25 equal to base over acid. 2 minus 4.25 is 10 raised to that is 0.005623413 over 1 is equal to base over acid, with the idea that this is our base form, this is our acid form. But remember, we're looking for ionized form. So the acid form is 1. So we're saying that our ionized is equal to 1 in this instance, whereas our base form is not. Our base form is whatever this is. So when we're doing our equation, this is where we have our 1 over this plus this, times by 100, obviously. 1 over total, because I'm going to write all that stuff down again. So we have 1 divided by this plus 1, times by 100, which gives us a percentage of 99.44% ionized. Which, if it kind of makes sense that if we're in an acidic environment, something that is more basic is going to be much more ionized in an acidic environment because it's going to pick up all those extra hydrogens. So it makes sense that if we're basic, we're in an acidic environment like the stomach, we should have a very high ionization energy. But if we get into something like the blood, which I'm going to use that one as an example, we have 7.4 minus 4.25 is equal to base over acid. And then that gives us an idea of 7.4 minus 4.25, and then 10 to that is 1,412.54, because I'm being lazy and rounding early, which I'm not supposed to do, is equal to base over acid. Once again, anything divided by 1 is the same number, and it gives us a ratio here to match our ratio over here. So once again, we're looking at the fact that the acid form is our ionized form. So that means that this is a 1 over the total, which is the addition of this 1 to this big number here, times by 100 gives us our ionization percentage. So 1 divided by that number plus 1 times by 100 gives us a percentage of 0.0707%, which is more or less 0.07%. So the idea is that's a very, very low ionization percentage in the blood. So it's pretty much going to be required to be carried by a carrier protein. With the idea that, like, because it's not ionized in blood, it can't just be in the blood. So, yeah. But I feel like these are really straightforward. Hopefully these videos helped people, the ones I made today. I don't really feel like I needed to, but yeah, I got asked, so cool.